What up, everyone? It is 7:30, so I'm gonna go ahead and start talking. I really don't expect that many more people to join, if any. For those who just got here to kind of give some background to what I'm talking about, yeah, I'll get you really quickly, Ruth, of course. But some of y'all probably noticed, some of y'all maybe didn't, but it appears that Michaelin messed up my links, but only for very nice, Jackson. A perfect grade? That's not me, honey. That is you. I had someone else who told me they got an A, and my response is, really? I'm so proud of y'all. My response is typically like, I can only lead a horse to water. Like, I give these sessions whether there's one person here or a million. It really is up to y'all to like utilize it and take what I'm saying and like turn it into a good grade. So like, well, yes, I do put some work into giving y'all information. It really is all y'all. Y'all are the ones that are coming here, taking the time out of your day to be here. So take that grade on you. You did that, not me. So be proud of that. Um, I did get a haircut, Ruth. I actually hate it. I don't really hate it, but my barber, um, he triple booked for a 1 p.m. Didn't even realize it till we were all there. And then so he rushed. So yeah, he really didn't cut like nearly any off the top. Pretty much all he did was cut the sides. So I'm a little annoyed with it. Oh, good question, Jackson. So yeah, I'm actually in Florida right now. Technically, I'm already on my Thanksgiving break. Yeah, I'm in Disney World specifically. It's 8:30 here, so my family's like already in bed. I'm sure I'm annoying them. But yeah, I'm in this bed because I have nowhere else. I'm praying the internet is good. But in saying that, I also don't have like my normal like dual monitors in front of me. So if I'm a little slower with things tonight, bear with me. But again, thank y'all for showing up. It looks like literally half of, I think only one email got correctly sent out with the correct links. Um, yeah, I'm not gonna throw Michaela on the bus. I'm just gonna defend myself here and telling you that I 100% sent the correct links. I already showed a few people here that the email that she sent me to see if everything on my end looked good did look good. However, somehow when she hit send to 5 different emails, it got messed up. Yeah, I mean, I'll even share it again. I mean, I'm not gonna throw her on the bus, so it doesn't really matter. But I mean, it wasn't me. But thank y'all for coming. 17 people is how many we have right here. That is, I think, my smallest session of the year. I even think my first session had more than 15 people. So I definitely think the emails is playing a bit of a part today, which is kind of annoying, kind of a Debbie Downer, but I did expect today to be a little bit of a smaller session anyways, especially with it being Christmas break or about to be Thanksgiving. Well, it is Thanksgiving break starting tomorrow. So yeah, 17 versus 190 last week. Exactly. Yeah, I'm literally still getting emails right now asking for the link. Um, so yeah, that's definitely laying apart. But I also, from what I've kind of heard, I feel like y'all all did relatively well on the exam. So give me like a thumbs up or something in chat if you feel like you did good, because I want to see that. I would like to, know. Yeah, exactly. Yeah, so fun fact, I believe, I'm pretty certain that I am the highest attended SI leader out of any course, like whether it's like chemistry, biology, organic chemistry, anything. Somehow, I don't know, but I have the highest, so that's really really cool for me. But yeah, it is weird to only have like 15 people here right now. So you've only missed two, Mackenzie. We stand. Um, yeah, I really don't have too much to say. I mean, please teach 1308. My boss had kind of asked me about it. I had done 1308 in the past, so I already had like the packets and stuff. I really enjoy 1307 though. I feel like I'm like really, really get it and can answer like literally any question over it. Versus 1308, I know like oh, I'm forgetting his name. Oh, I'm embarrassed. I don't know his name. But one of the SI leaders is, I mean, he would be better. He's way better at 1308 than I could truly offer you. Like I know the course, but the dude's like beyond what I could comprehend from 1308. So I think you'll be in good hands. I think I clearly have a really, really good grasp on 1307. I love it. I think it's an important class to like really teach. So I don't know. I may not. I may. It just kind of depends on really my boss and really what I end up, kind of wanting to do. Yeah, I do. I mean, that's the goal is to make him fun, and I think that's why it's really important a little bit for me to stay in 1307 because 1307 is extremely hard, and almost everyone has to go through 1307. And again, almost everyone does really bad. So it is really important to like kind of have like that course that no one really likes be a course where I can kind of make it fun and make it entertaining and educational at the same time. So I'm not decided yet. But I'd say I wouldn't hold my breath is really what I would say. I'm really, really enjoying 1307 right now. Um, but yeah, I will keep you posted, of course, Ruth. Let's go and jump into it. Today's session, I don't really know the length of it. At one, um, earlier today, I was kind of like, maybe I'm a little too in over my head. Like maybe I put way too much on this packet. And then another part of the day, I was like, no, I'm gonna fly through this packet. This is just no math or anything. Like I have to speak. So I'm not really sure whether we're gonna end early or late or what, but I am at 8:30 right now, and this session goes to 10. So I'm personally not gonna want to stay really too much longer past 10. Hold on, let me drop myself the packet really quickly to my iPad, and then we will officially get started. All right. But how is everyone else doing today? How many of y'all are still on campus? That's probably a better question. If you are still on campus, at least know that tomorrow is your last day, and then after that, you're you're on break. While when you come back, it's finals and we're done. So like, we're at the end here, people. We are literally at the end. Today is my last individual SI session. Next week I'll be starting exam prep. So yeah, people, we're at the end. I'm pretty lit for it too. But okay, officially got my packet on my page. So let's your parents have COVID, Emily, and I'm so sorry to hear that. I mean, I truly am sorry to hear that. I pray for a speedy recovery and everything, truly. My professor just got COVID as well, which was kind of shocking and a little scary because he's my Spanish professor, and there's only like literally only like 15 of us in the class. I was like, bro, you were like kind of close, like in contact with me, but I think I'm okay. I mean, it's not like I really came in contact with him. He's just in like a close vicinity to me. Why is my screen not sharing, y'all? It's gonna be one of those days. I can already tell. Sorry. I don't know why my screen's not wanting to mirror right now. Give me a second. That's gonna be a really, 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 really big problem if it doesn't want to share. Oh Lord. Okay, come on. Third time's the charm. Let's try it. 3, 2, 1. It's not working. Okay. Great. Fun stuff. I'm a little shook. What the? I have no clue why it's not sharing. This is literally the first day of my 24 SI sessions. My iPad's refusing to work. I don't know. I hate it here right now. I'm so annoyed. I'm literally like embarrassed, shocked. I don't understand what's going wrong. Let me try. Let me try another way. Hold up. I don't know what's happening, y'all. I don't know why it's acting like this. Give me a second. I think I have a solution. Give me a second. I think I'm gonna be smarter than the computer today. I do not know what's happening. Even an HDMI or like a HDMI type deal is literally my computer's registering it, but my iPad is literally acting like it has never. I'm gonna restart my iPad really quickly, y'all, and I'm just gonna go ahead and put up. I'm gonna go ahead and go start going through the packet with the key on the screen because the first part is fill in the blank anyways. My computer, literally my iPad's not even giving me the option to restart it right now, so pretty confident it is 100% my iPad. Yeah, well, sorry, Julia. It's took on my iPad is what I'm trying to do. But okay, I'm just gonna put up the freaking answer key really quickly. Okay, let's jump into this. I'm so sorry, y'all. I don't know what's happening. Can y'all see this though? Let me know. I don't know why my iPad's not connecting. It's the most bullshit I've ever seen. Good luck. Good luck, Laura. You got it. Take your time. Pound it out. Yeah, I mean, I've never had, this is literally the first time in my whole, I've used an iPad for 1308 as well, and I've never had the iPad give me trouble. So it's just gonna be one of those days, and that's okay. Okay, let's go ahead and look at this though. So we're starting on chapter 11. Chapter 11 is extremely conceptual. It's gonna be one of these chapters where I'm pretty much gonna tell you, like, probably a lot of this stuff is gonna, a lot of this stuff tonight is gonna be a lot of repeating sentences. That is kind of because chapter 11, again, it is extremely conceptual, but in saying that, because it is so conceptual, typically the first time you hear it, because it's like just a word, or it's kind of like a wordy description of a physical process, typically the first time you really read it and try to comprehend it, you really don't. Even the second time, it's really still pretty abstract. It's really only that like third or fourth time you're like, oh, like I see how it's clicking. So tonight it may feel like a good bit of repetition, but that is important. Once it starts to feel like I'm repeating myself a lot, that's how you know you are learning, because you're starting to remember it in your head. So yeah, just kind of want to preface a little. Okay, so chapter 11, 11.1 is valence bond theory and orbital hybridization. Again, kind of a lot. One thing is we're going to be talking about hybridization of orbitals, basically two orbitals coming together to make a new orbital. All right, so the basic principle of VB theory, or valence bond theory, is that a covalent bond forms when orbitals of two atoms overlap, excuse me, and a pair, that's important, a pair of electrons occupy the overlap region. So this is just kind of like a new definition of a covalent bond, but mainly looking at those, mainly the orbitals, and how specifically, if it'll let me highlight here, perfect, how those two, so the orbitals of those two atoms overlap. And as we'll see in a second, that's actually what makes the bond, is those orbitals, which, you know, has, as we said in the past, like an s orbital is just a sphere for like hydrogen. A p orbital is kind of like a dumbbell, kind of like a figure eight, but there's technically three of them, because we know in our p block we have, you know, three squares for our electron diagram with like the up and down arrow type deal. So yeah. All right, this next point is that the overlap of the two orbitals means their wave functions are in phase, so the amplitude between the nucleus increases. I wouldn't say this is like too much conceptual you really need to know. I would really just say this is more of a trivial fact that is specific to orbital overlap. So just kind of note the amplitude does increase. This is because basically if we have construction or deconstruction, basically if one, you know, one wave is high and the other one's low, they equal out to just zero. So basically there would be, we could say in this instance that there would be no attraction, but this amplitude, basically they end up going the same wave. And so because they are already in the same wave, going at the same speed, they end up doubling when they meet. And they, because they're staying in that same wave, just a higher peak, they essentially are acting like they're fine, because it's kind of that speed that they're used to as singles, but we're just increasing that amplitude when we overlap, versus if we had deconstruction, we would end up with that, just that zero, and they would be totally out of whack and there would never be a bond. So just kind of describe how that, you know, the increase in amplitude does relate to forming a bond. All right. So some important things to remember when thinking of orbital hybridization. Again, orbital hybridization is combining like an s orbital, which is a circle, with a p orbital, which is a dumbbell. We'll hybridize them. So as the exclusion principle requires, like the Pauli exclusion principle from last test, the space formed by the overlapping orbitals has a maximum capacity for two electrons that have opposite spins. So again, the opposite spins part is relating back to the Pauli's exclusion principle. But this is specifically talking about when we overlap orbitals, we still can only have a max of two. So we're used to thinking about it for just a single atom, let's say just, neon or whatever we want to say. Think of any element you think in your head. We're used to two electrons per orbital. For example, in the p orbital or the p block, we have three orbitals. Each of them can have up to two electrons. Hence, there being six elements in the p block. Um, However, when we are combining two orbitals, we won't end up having four electrons in an orbital. We will still only have two. But how can we have two if there's already two present in one? Hmm. So that's kind of where the hybridization comes in. It's kind of like taking away one of those electrons, which again, we'll see a bunch here in a second. Alrighty, so a p or a d orbital, not the s. Note, not s. So the p and d orbitals are involved in a bond, or sorry, a p or d orbital involved in a bond. So a p or d electrons contributing to a bond. Um, those orbitals are oriented so as to maximize overlap. So that's kind of like a very conceptual, even like, I mean, I kind of understand what it means by maximizing overlaps. We'll see some visual examples a little bit later. But I would really say that this is kind of a more important statement. I could like truly see them like just testing that just which two blocks or which two orbitals increase or seek to maximize overlap. In that case, it would be the p or d. And we'll see a little bit more about that later. It's kind of has to do with how they're more of elliptical versus our s orbital is more spherical, so it's just equal in all directions versus those p and d's, because they do have those kind of like ellipses coming out from the center. That because it's long, it is trying to seek maximum overlap because it's geared towards one specific region versus spreading out your electrons just kind of all over randomly. So, alrighty, the greater the orbital overlap, so the more we have two things kind of like literally right on top of each other, the closer the nuclei are to the electrons, and the stronger the bond. So how I kind of like to like just think about this is if we have two hydrogen atoms like this, right? I'm gonna just go ahead and let's say like this, the fist. Both of these are the nucleus, the positive parts of whatever, let's say helium or hydrogen, whichever ones. And let's say like our outer cloud kind of comes out here visually. Okay, so we got like two of those. Right now, they probably don't have any overlap. I know it's kind of visual, but as we kind of bring them closer and closer, we'll kind of see that center area, there will be overlap of those electron orbitals. So again, if this is the center and this is kind of like the outer shell, and the other outer shell from the other hydrogen is over here, the closer and closer we get them together, they will eventually start to make that kind of like Venn diagram type deal. And that little center part is that overlap. The more overlap we have, the stronger the bond as well as the closer together. And I think that kind of makes sense, especially with this visual I just did. You can literally see that the more overlap we create is directly associated with the proximity of the atoms. And then kind of going back to last test, we had said that the closer electrons are to the nucleus, the stronger the bond. So kind of same thing here. Just the closer two things are to each other, the harder they will be to pull apart. So therefore, the stronger. Alrighty. Let's see. The valence orbitals in the isolated atoms become new orbitals in the molecule. So let me read that again and let's break it down, right? Okay, so the valence orbitals in the isolated atom. So again, let's maybe not use hydrogen or helium, two heliums together, but let's say we have hydrogen and chlorine. So those valence orbitals, those most outer layer, typically that 2s2, 2p6, which would be like neon, I believe. That's going to be its valence orbitals, that s and the p. So it says those valence orbitals of those isolated atoms, so the valence of the hydrogen and the valence of the chlorines, become new orbitals in the molecule. The molecule is HCl. A molecule is combined. Isolated atoms are singular. So we have valence orbitals right now, as we have been learning about, but once we become that molecule, once we finally join together, those are going to create new orbitals, which we're going to, oh, I already have the answer on the page. I forget because I'm not used to doing it like this. But this process of mixing these orbitals from the valence orbitals from isolated atoms is called hybridization. So that's really, again, what we're going to be talking about pretty much all today is hybridization. Taking an s orbital from a hydrogen, and how is that going to have to bond with a carbon or chlorine or XYZ? Again, we're going to have to hybridize some of those orbitals. All right, and the new atomic orbitals are called hybrid orbitals. Okay, so that's kind of that. While I'm kind of at a good spot, I would like to know if you have any questions thus far. That was kind of the more conceptual part. We're about to be going in to some more like written examples, but let me try to see really quickly if my iPad will share now, because I would really 1010% prefer it to be shared. Come on, screen mirroring, please, please. Okay, I don't know. I literally have zero clue. I have never had my iPad not want to connect. But it looks like today is the day. I know, Ruth. I know. Ruth, you've literally been to all my sessions. You literally know this has never happened. And I have my iPad right here, y'all. Hold on. I just want to prove that I'm not even like lying, like not even trying to like bail myself out. Literally, the screen mirroring thing has nothing. So I literally don't know. I don't know the fix. I'm not going to sit here in the SI session and try to fix it. Yeah, I don't. It's because I'm in damn Florida. Everything's got to go wrong weird here. But okay, let me go back to just sharing the screen. I feel like some of y'all maybe like it because my answer key's just like right there in front of you. But it's definitely not my preferred method. So, okay. Let me go ahead and get the chat back up really quickly and we'll keep moving. All right, so now let's look at specific types of hybrid orbitals. The iPad is ready for Thanksgiving break. Clearly, I was not ready for her to be so done, but I'm with her. Okay, so we're gonna have pretty much, I'm really specifically gonna talk about 3 types of orbitals today. I will go ahead and tell you the other 2, but I don't by any means think they're gonna test on the other 2. So today we're gonna be talking about the SP, the SP2, and the SP3. We do go into SP3D1 and SP3D2. However, they're really not super relevant, and if you just kind of follow the pattern that I'm doing for the SP, SP2, and SP3, we will you'll be fine. And if you want me to work an example later on with the SP3D1, easy too. So, okay, yeah, I'm sorry y'all for the iPad, but I think it may even be better for this session even to have it like this, just because I feel like maybe you can see some of my thought processes on stuff I do. But you kind of see the T of me like at times being like lazy with copy and pasting. Like for example, you'll see this thing copy and pasted like 1,000 times in a second. Okay, so the SP2, this is BeCl over here. It is a Monday, and it 100% feels like a Monday right now. Over here, I do have BeCl2 over here. One thing to kind of note, I didn't want to make you draw the Lewis structure because I feel like this is kind of a harder Lewis structure, simply because it's one of the cases where beryllium or a certain atom won't have to have a complete octet. It's, in this case, just fine, which is for electrons. I believe that when you find the valence electrons for beryllium and chlorine, you get like, I want to say 18 or 16, and then once you subtract those 2 bonds, you're left with 12. Exactly, yeah. So it's 16, and then you're left with 12 dots to put around, and then 6 for the left chlorine and 6 for the right chlorine. So you're left with 0. So if you were to try to do the Lewis structure, you'd probably see pretty quickly that beryllium doesn't need any lone pairs. But I just want to give it to y'all just because. Okay, but again, The electron geometry shape is linear. We're not just saying it's linear for BeCl2. We're saying all all sp hybridizations are going to be linear. So that's just kind of something to see in your head. Anytime you are given um, a linear molecule and they ask you what the hybridization is, just from seeing that it's linear, you should quickly be like, ah, sp, because you know if it's linear, it's sp. Easy as that. Okay, so because Be has a complete s orbital, meaning that there are no unpaired electrons, that is because if we go to a periodic chart, um, I hate that it's like this because I can't flip back super easily. But beryllium, as we see, it is a 2s2. We're saying that it has a complete s orbital because that s2 and s orbital only can have a max of a positive half and a negative half electron, which it does. So because beryllium has a complete s orbital, meaning no unpaired electrons, we wouldn't expect it to form bonds. Because what we have been learning in the past is that um, kind of an unpaired electron is kind of the scenario to form a bond. And we kind of saw this in the past in kind of several different cases where when we were doing like the electron dot configure or yeah, the electron configurations, such as like this 2p thing. For carbon in the past, we had specifically for carbon, which is actually right here. No, carbon is, let me show you the exact example just so I can okay. So this example right here is carbon with this left side. Carbon has a complete 2s2, and then it is 2p2. So there is 2 electrons in the p orbital. And so just from this, in the past, we had said that it looks as though it can only form 2 bonds because those 2 unpaired. But then that's when we learned about the Lewis dot structures, and we saw that you can put 1 dot on each side of carbon, and that was more accurately representative of that carbon could form 4 bonds. Do we recall that the Lewis dot structure with um, the 4 dots around the C was representative of the amount of bonds it could make? Yes? Okay, perfect. And again, that is representative. Those 1 dots on each side of the carbon, that is a unpaired electron, versus when we had a full octet of electrons, we would put 2 dots to a side, right? Because it's paired. And so in saying that, that's kind of, again, just explaining why we would expect beryllium to not form any bonds, because it has a complete s orbital. So there's no unpaired electrons, so we wouldn't expect bonds to be formed. However, valence bond theory proposes that 2 non-equivalent orbitals of a central atom, that's more the irrelevant part, but 2 non-equivalent orbitals, 1s and 1p, mix and form 2 equivalent sp hybrid orbitals that are oriented 180 degrees apart. So as we kind of see it down here again, in beryllium chloride, the beryllium atom is sp hybridized. So let's depict it and let's kind of talk about what we're talking about. So specifically beryllium, we do see that it has a complete an s orbital. So again, we wouldn't expect it to form bonds. However, it does, as we see literally, if you just Google beryllium chloride, it does form bonds. So how does this happen? In reality, in the true life, we will have a hybridization. Basically, what's going to happen is that one of those s electrons is going to basically realize that it's going to be attracted. It is going to want to form a bond. So pretty much what's going to happen is, I kind of drew it here, but we understand that the s orbital, the 2s, is slightly closer to the nucleus than the 2p orbital, right? So it's kind of how I depicted it here, is the 2p is above the 2s. However, when we hybridize, we're going to end up with a level about a little bit in the middle. And again, specifically, the p orbital, because it's going to go in the middle, it's going to take on a slight bit of the shape of the s orbital. Quite literally, their two shapes are going to kind of combine a little. And they're going to do that so that it kind of tricks the electrons into thinking at times, well, I'm in the s orbital, but I'm also in the p orbital, which lets me bond. So when we're doing this, what's really happening in reality is, to form an sp orbital, all we're going to do is just use one singular orbital from the 3 possible orbitals of the 2p and bring it down just to get rid of one of those electrons. What we're going to see as a trend is that pretty much we're going to have enough boxes for the SPs Oh, it's not letting me highlight the SPs. But down here, we're gonna have enough boxes for the SPs to basically have an up arrow for each one so that we can make the respective amounts of bonds. So again, here we see that BE makes two bonds, one to Cl and the other one to the other Cl. So again, two bonds, we need two unpaired electrons. So in saying that, we see here in these two orbitals, we have one unpaired electron from this one sp and one unpaired electron from this one sp. The other orbitals from the two p's, they don't hybridize. They remain unhybridized, and that's because in the p orbitals, again, it is a dumbbell, and the fact that it is like an infinity sign kind of up and down. There's an infinity sign side to side, as well as there's an infinity sign kind of like diagonally. So there's three of them. It only needs one of them to contribute it, versus the other two can contribute or can continue as normal. So again, we're only going to use up as many p orbitals as we need to form enough bonds. So because we have one s orbital currently, and we need to make two bonds, we have one s, so we need to pull down that one more p. Okay, and again, we'll see this a lot more, but I'm just trying to give it in kind of, I'm not going to say layman's terms, but I'm trying to like oversimplify it a little bit, not give too much specificity right now, to try to maybe kind of see the pattern at first. But again, from the sp orbitals, we see that there's two unpaired electrons, which is representative of being able to form two bonds. Okay, I know maybe some of us are a little stressed, but let's go ahead and look at sp2 before we ask any questions, because I think you'll start to see the pattern pretty quickly. Again, this is a very, very conceptual concept, but if you can kind of relate what's happening with the box diagrams to what is being said in the top, you're gonna be good to go. Okay, so sp2 hybridization. Again, that is going to be representative of the BF3. Also, Julia, I know you had asked if you could leave at 8:45. I'm totally good if you still want to do that. I'm fine watching the chat room. Don't you worry. So, oh, I forget. It's 9:02 for me right now. I forget it's 8:02 for you right now. Never mind. Leave whenever though. Sorry. It's 7:02 from, yeah, again, I'm in Florida, so it's 8:02 for me right now. My essay had said that she needed to dip out a little bit earlier, so I was watching the time just to like make sure that I'm on top of it. And I saw that she was still here, so I was like, "Oh, you don't need to stay." But then I realized, she's probably still in Texas and still has 45 minutes left. So, my bad. Okay, but sp2 hybridization. For this example, we will be using BF3. BF3 is one that you should be starting to realize with the Lewis structures. I believe that they may have even tested you on this. This is one that I had kind of said in the past. It's kind of like a staple for trigonal planar, at least. But again, this is the BF3 molecule. It is trigonal planar. And one more thing to say about trigonal planar is, again, anytime we have an sp2 hybridization, it is going to be. Wait, yeah, Ruth, where are you? Where are you from? If it's 7:02, that didn't even click in my head. Um, but please do pay attention that this is electron geometry shape. sp2 will always be trigonal planar electron geometry, but not always for molecular geometry. Because again, looking at here, this is of course trigonal planar for the molecular shape, but had that fluorine that isn't currently highlighted been an electron pair, our electron geometry would be trigonal planar, but our molecular geometry would be bent. So just kind of keep that in your head, that electron geometry with sp2 is associated with trigonal planar, and it will always be trigonal planar. Okay, so let's talk about it. So in this case, mixing one s and two p orbitals, again, because we're making three bonds. So initially, of course, we're always going to have that s orbital, and so that s orbital is going to allow us to make one bond, but we need to make two more. So we're going to need to hybridize to have three sp2s. So there's an orbital for the s. We pull down a p and pull down another p. Each of those can make a bond representing the fluorine, the b to f. Okay. So mixing one s and two p orbitals gives three sp2 hybrid orbitals that point to the corners of an equilateral triangle, again, a trigonal planar, and their axes, of course, are 120 degrees apart. While I'm thinking about that, did they test y'all a lot on on the angles for the geometries, because I had told y'all I didn't think they were going to test y'all a lot on them. I thought it was gonna be a little bit too trivial, but let me know. A little? Okay. Hopefully not like too many. There's only 25 questions, a tiny bit. It was like one question. That's what I figured. I would figure there would have been like 3 or 4 on, or maybe out of 25, maybe not 3 or 4, but maybe like 2 or 3 for like electron molecular geometries. But I wouldn't have thought many of the of the degrees. So I'm glad that there's only one question. That makes me feel good, because I know the previous test before this last one, I had told y'all to like memorize the solubility rules, and y'all came back and were like, they weren't there. So I was really scared that I was gonna be like, yeah, y'all don't need to know this, and y'all be like, it was everywhere. So that makes me at least feel good that at least this test I was maybe a little more accurate, or at least didn't give y'all something to memorize that wasn't on there. So okay. Continuing on, also, can y'all see the chat box on my screen while I'm sharing? Just no, y'all can't. Okay, perfect, 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 perfect. Okay, all right. Continuing on. So again, 120 degrees representative of that trigonal planar. The third 2p orbital remains unhybridized. Again, same thing for the previous 2p orbitals. Or sorry, yeah. The previous 2p orbitals, they remained unhybridized. They didn't take on any s characteristics. Yeah. So each half-filled sp2, again, we want to half-fill the sp2 orbitals so that they can bond. That's the whole point of even hybridizing, is to get them half-filled so we can fill them to form a bond. So each half-filled sp2 orbital overlaps, oh, see, I literally just said it, and here it is, overlaps the other half-filled 2p orbital of a fluorine atom. So kind of going into that, fluorine only needs to make one bond, as well as we'll see a little bit later. We'll see some more examples, but because fluorine is a 2p5, it already has a at the very end of its electron geom of its like boxes for electron geometry. It's up, down, and then just up for that last 2p orbital for fluorine, and so that is why um, each of these half filled can perfectly match with a fluorine, because the fluorine doesn't need to hybridize. It already has a half filled p orbital, which perfectly supplements the sp2s, as well as the sp2's electron perfectly supplements fluorine to a full octet, or a full p orbital. So again, the whole point is to get half with halves to make a whole. Okay. And then the 6 valence electrons, which the 3 from the boron and 1 from each of the 3 fluorine atoms, those will form our 3 bonding pairs. Again, to form a bond, this is kind of what I'm saying with the half and half. A bond is always comprised of 2 electrons, and specifically in a covalent bond, that is going to be more of a sharing. So it's going to be one contributing from one nonmetal and another electron contributing from a different nonmetal. So we have a 1-to-1 making that bond. Okay. So now let's take a little bit closer look at the true hybridization of beryllium in the orbital box diagrams to see what's really happening, or really mainly pay attention to the pattern. So this first part over here on this left side, this is the orbitals that we have been typically doing in the past. We understand that boron is a 2s2 2p1. So in saying that, we have a 2s2 here, a full 2s, and then for that 2p1, we'll just have that one singular electron in one of the 2p orbitals, one of the 3. Again, we know that boron is going to want to form 3 bonds. So in saying that, we have 1, 2, and 3 electrons. Each of those we know we want to get into orbitals by themselves, so that when we want to form bonds, we just match them up. So in saying that, pretty much the simple way that I like to explain it is that we're literally just going to pull down 2 p orbitals to basically account for the number of bonds we're making. We're making 3 bonds, so we should have 3 orbitals, right? Same thing up here. We're making 2 bonds, 1 to Cl and 1 to Cl, so we want to have 2 bonding orbitals. So we only pulled down enough to give us enough orbitals for bonding. So again, I took 1, 2 p orbitals, pulled it down, left that third 2p orbital at the top, because again, it has no need to hybridize, it has no wish or electrons to bond, so it's just going to remain as is. Nothing's present in it, so we can just assume it's in space as we would expect. Okay. And again, when we do this, we do want to go ahead and redistribute those electrons. Again, kind of going back with that Pauli, or I think it may be Hund's rule. But we must have at least one electron to every orbital before we can start to pair them. That is the same thing we're doing with the sp orbitals. Again, while at first we do have a up down for the 2s, when we mix them, we're creating a whole new orbital. We're creating an sp2 orbital. And so when we create that sp2 orbital with 3 specific orbitals that can have electrons in them, we still want to follow those general rules of 1 electron to every individual orbital before we match them. So that's why we still have just 1 up arrow to every sp2, because again, we've created a whole new orbital, so we still want to go by those same rules of 1 up arrow or 1 positive spin first before we start to match anything. Okay, how are we doing thus far? Are we doing pretty good? Doing good? Okay, thank you, Laura. Alrighty, one more example, and if it's not completely clicking yet, hopefully this last one will be good. And kind of something I do like to say, again, we want to have enough orbitals for amounts of bonds. So as we're kind of be seeing here in a second with this sp3, um, and sp3 is always going to have 4 electron groups around it. So a super easy way on the test, which they're probably going to have one like this, they'll probably just give you an element, like they may even give you something like CH3 or CH4, and just say, what is the electron geometry of carbon? All you have to do is just count the number of bonds and electron groups, or you can just say, yeah, the amount of electron groups. And if there's 4 electron groups, it's sp3. If there's 3 electron groups surrounding the central atom, it's sp2. If there's only 2 electron groups surrounding the central atom, then it's just sp. So that's kind of one way that I like to think about it. But yeah. I didn't go to Gordon's lecture today. I was in like riding rides in Disney World. I kind of feel guilty about not going, but I didn't go. It seems a lot simpler than, yeah. I mean, it's an extreme. Okay, I will say it's an extreme. He looked hungover. Oh, that is tea. Someone said he always does. I'm dead. Oh, whoever Joyce, you're wrong for that. But to kind of cut him some slack, hybridization is an extremely complex topic. There are a million and one details that do go with it. I'm trying to just explain it in a simple form, that kind of clicks the pieces and connects it to the past test. Because you're only going to be seeing this on the exam, and so they're going to give it in reference to things that are applicable to the past exams. They know that this is fresh, and while I do expect you to know it, they understand that it is a lot of times. So I'm pretty much presenting the information in a way that will get you the answer right on the test. I'm not here to give you every detail. So Uh, we love him. He's just frustrating. Sometimes he's growing on me. I I don't know. He stopped canceling classes much, and I feel like his lectures have gotten a little bit more true. There was a certain point where he, in my opinion, had said some stuff wrong, but yeah. Who is this Gordon? Yeah, exactly. Okay, so the sp3 hybridization, I put CH3. I'm pretty sure I meant to put CH4, or which is just a carbon. I didn't draw it out, but which is just a carbon with hydrogens on each side of it. I'm almost certain. Yeah, even here I said the 4 CH bonds. So I definitely meant CH4. Go ahead and correct that in your packet if you would be. I wouldn't think it. No, your test is definitely not going to ask you to draw out the orbitals, but understanding what's happening with the orbitals. Isn't he an honors professor? No, he's just normal. He's just a new professor. He's like kind of got thrown into it. No, you won't. But again, going back to this, you won't have to draw these out, but you may have to interpret them. They may say like they may give you just like these orbitals and say you're forming a compound with 3 bonds. What should the hybridization like be? So in that case, you just have to say sp3 because you would understand that there's 2 electrons here, 2 electrons here, and each of them would want to form a bond, so they would each have to be respectively in their own singular orbital. So if they gave you like literally, they could just give you this left side and say like what hybridization should be, and you should be able to say sp3. So that'd be like one of the ways. But yeah, I don't expect them to make you draw out the orbitals. Today, I will be making you draw out the orbitals. But the goal is if you can draw the orbitals here, you will be able to interpret them on the exam, correct? So yeah. All right, so for sp3, our electron geometry shape is always going to be tetrahedral. Again, I think sp3 is going to be one of the easiest cases. It's going to be with either 4 bonds, 3 bonds, and an electron pair, 2 bonds, and 2 electron pairs. Yeah, those are the 3 cases. Again, any 4 electron groups surrounding a central atom is always tetrahedral and is always sp3. Okay, so let's look at the mixing of it. So mixing 1s and 3 p orbitals gives 4 sp3, kind of going with what we expect, that point to the corners of the tetrahedron, which I believe are like 109.5 degrees. The carbon atoms in methane, which is CH4, is sp3 hybridized. And that's, again, because we want to form 4 bonds to each hydrogen, and so therefore it must be sp3 because an sp3 represents 4 individual or orbitals, each with 1 electron, which can therefore make 4 bonds. Okay, so it gives 4. Oh, sorry, we're down here. Methane is sp3 hybridized. Again, from that sp4, it's easy to see. Its 4 valence electrons half fill the 4 sp3 hybrids. Again, once we make those hybrid orbitals, we do want to do 1 to each before we match them. In which they overlap the half-filled 1s orbital of 4 hydrogen atoms to form our 4 CH bonds. So kind of referencing back earlier what I was saying about fluorine, on how fluorine is a 2p5 element, and that we understand that that last orbital of fluorine isn't completely full. It doesn't have an up and a down, and that is what allows us to have a sp half orbital bonding with that unpaired last p orbital of the fluorine, is the same case that we're having here with the C to H, except that the hydrogen is in just the s orbital. The main thing to be noting or to be realizing is that we still must have just an unpaired electron. It doesn't matter whether the electron is in the S, the P, the D, or the F. The criterion is still that we want to have an unpaired electron. So in this case for hydrogen, we don't have to hybridize hydrogen at all because first it's only an S. It never even reaches to a P, but it is already unpaired. Versus carbon, we do have 2 paired electrons in the s orbital, and we want to form 4 bonds, so therefore we have to get rid of that. The atom's literal way of getting rid of the 2 electrons in the 2s and making it to where they can bond is just, again, combining that p and that s, kind of bringing them closer together and changing their shape to where it's got a little bit of properties of both, and they have enough orbitals for 1 to be in each. So again, all I'm going to do is literally bring down enough p orbitals that when I take away one of my 2 s's, I have enough to where 1 goes into every single orbital, which you will see comprises, in the sp3 case, the entire p orbital. Again, and at the end, you should be seeing 4 boxes representing the 4 bonds because each box should only have 1 electron in it. So again, this is every single one of these is an sp3 orbital. Okay, I'm literally putting the practice up on, I'm literally putting the answers up on here. Maybe I didn't put beryllium fluoride though, so maybe we can practice that one. But let's look at oh, sorry, I'm not reading the text box. I don't even think I need to. I think we're doing good. Okay, perfect. So I'm gonna go ahead and just look at this first one with y'all, just because why not? I've already shown it anyways. I'm sure y'all have looked at it, and then y'all can try the next one on your own. So in this practice problem, it's saying use the partial orbital diagrams to describe how mixing orbitals of the central atom leads to the hybrid orbitals in each of the following. So it's kind of wordy, but basically this is what I'm looking for. Basically, I want you to take the initial orbitals, hybridize them, and basically just point out because we have 4 orbitals now, that allows us to make 4 bonds. Um, and then I also wanted you to point out here for hydrogen that hydrogen is unhybridized. It is just going to be that 1s, and that 1s1, just that up arrow of the s, will be combining with um, our respective sp3s here, so that we have 1 up and 1 down from that s orbital from the hydrogen. All right, I got a question. Can you erase it and put the can you erase it and put the back button to make it come back? I didn't need. Oh, I mean, I'm not on my iPad. I can't erase it all. This is just a PDF document. So it's just stuck. Yeah, it sucks. I don't know why my iPad today decided to crap out. But yep, unfortunately I can't erase. What is on here is I literally can't write or erase. Yeah. Yeah, no, I know what you're saying, but yeah, I'll just try to be more diligent with like making sure I don't show the answers. Um, but again, starting with the carbon, you should know that carbon is a 2s2 to p2, representative of its valence shell. Here is what the orbital diagrams look like. Again, you were literally just tested on orbital diagrams last test, so this first little part you shouldn't really be struggling on. However, the mixing, again, is the new thing really. Also, while I'm thinking about it, I know I'm holding my pencil, so maybe kind of deceptive. I just fidget with it. But can you see my cursor as I'm like circling things? I'm assuming you can see when I highlight stuff. You can. Okay, perfect, great. Okay, good. Then I'll just keep pointing at stuff like that. Okay, but again, um, because we do see that carbon, I went ahead. I was going to give you the structure anyways, but we do see that carbon does form 4 bonds. So therefore, we want to have 4 orbitals half filled, which is representative of that sp3. Oxygen here is gonna. This is a fun case. This is probably the first case that we see an sp3 hybridization without 4 atoms around it, really. So as we see here, we have oxygen and it's bonded to carbon and hydrogen. However, it does have those 2 electron pairs. Those 2 electron pairs are just they really are just as relevant as the 2 atoms, and we kind of harped on that a little bit um, in the past as well, specifically last test, that for like electron and molecular geometry, we still count those electron group or those electron pairs as an electron group. And same thing for hybridizations. For like sp3, we want to make sure that we have 4 electron groups, and an electron group can comprise of an electron pair. So just from looking at oxygen, if you just saw there was 2 bonds and 2 lone pairs, you could quickly say it's sp3. Easy. I see 4 electron groups, it's sp3. But really the thing that I want to be looking at today is making those hybrid orbitals. So that first thing you should have done is gone ahead and made your orbital diagram for the valence electrons of your oxygen. There are six valence electrons for oxygen, so I went ahead and did for the s orbital, I did 1 up, 1 down, and then for the p, I did up, 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 and then 1 down. That left me with kind of this kind of out of ordinary thing from what our trend has been in the past. Pretty much in the past, from like up here, what we were looking at. Oh, sorry, let me my chat for me. Pretty much what we had been seeing is that like we have 1 up and 1 up, and I've pretty much just been bringing those down. I've been doing that like visually, just like so you can see that the ones with that electron comes down and that one that's unfilled lays up. But what I was also had been kind of saying is that we want to have 1 unfilled orbital for each bond. And so basically I didn't give a super complex p orbital thing because I wanted to explain how we kind of shift things easily. But here we have a little bit different amount of electrons, but as far as creating our orbitals, we want to go by that same bonding concept. We know that oxygen has 4 electron groups, meaning that it has the potential to create 4 bonding pairs. And so because of that, we want to go ahead and at least give it that sp3 geometry, and which says not only do we have 4 electron groups, but we also have 2 electron pairs in which no longer can we form a bonding pair because it's no longer or it is filled. So in saying this again, I have a full 6, the 2, and then 1, 2, 3, 4 for the oxygen. I know that we want to have 4 orbitals at the end because we have 4 electron groups. Therefore, I know it's going to be sp3, so I go ahead and give it the 4 orbitals. Going by Hund's and Pauli's exclusion principles, at that point is when we go ahead and fill it in with up, 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 and then down, down. What does it say above the arrow? Mix. Yeah, exactly. Yeah, it says mix right here, just so that we're officially mixing the orbitals. But yeah, exactly. So once we know that there are 4 electron groups, that is representative of 4 electron orbitals. So we want to go ahead and give it that sp3, or representative of these 4 boxes, and then continue with those rules we've had in the past of Pauli's and Hund's, up, 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 then down, down. And then you can see perfectly that it totally accurately represents oxygen, because as you see here, as I had wrote, these 2 up and down pairs, again, each square is representative of an orbital. And so an up and down is a full orbital. And so we have 2 full orbitals representing those electron pairs. Because if we kind of remember the last test, electron pairs do in fact they do sit in electron orbitals. And so just from this representation, we see that 2 of the orbitals are filled with paired electrons. And because they're already paired, we know that those are lone pairs, because a bond must come from half-filled orbitals. So these 2 half up arrows, I wrote forms 2 bonds, and that's because, again, those, we not only do we see that oxygen is going to bond to carbon and hydrogen, but we do know that is the, the true set of rules is that a half-filled orbital allows us to form bonds. Okay, hope that made a little sense. Ask questions on the oxygen if you need it, though, because I understand oxygen may be the first case where it's a little wonky. Okay, but then the hydrogen is just going to be unhybridized. It's a 1s1. There is literally no potential for hydrogen to ever hybridize. And so for that case, pretty much we're always just going to have an sp3 to a hydrogen, or to an sp3 to an s orbital overlap for our hydrogen to carbon, as well as our oxygen to hydrogen. So yeah. Okay, we are kind of running low on time, so I'm gonna go ahead and just show you the next one as well. I would assume a few of y'all probably tried to work it, I would hope. But I do want to talk about the next stuff because I think it's almost more important than this stuff. So, beryllium fluoride, I did plan on giving you the Lewis structure, which is here. It's very similar to the I believe it was BeCl2 that we had earlier. Again, from this, let's just look at beryllium and fluoride's orbitals. So beryllium is just going to be it's just 2s2. It's just a period 2 element. And so for that reason, its valence orbitals we represent as this, just that 2 electrons in the 2s, and of course 0 electrons in the 2p. The only reason I put the 2p up there is just so that we have it there, so when we go to form our hybrid orbitals, it makes a little sense. Okay. From not only do we only have 2 electrons, because we only have 2 electrons, we do it is kind of a little, I'm not gonna say easy to see, but it shouldn't be too much of a jump. My essay just got kicked out. It shouldn't be too much of a jump to realize that can only, when it's hybridized, it can only ever be sp, because it doesn't have enough electrons to donate to have more than just 2 orbitals. So for example, and as well as it only forms those 2 bonds. So when we mix it, the only thing we can ever do is just pull down 1 p orbital, so that we can pull one of these, specifically one of the down arrows, to form another orbital, which gives us that ability to pair. We're going to see this most of the times for our left side of our table. It's typically going to be our noble gases and covalent bonds that we start to see. The hybridizations can get pretty crazy, but pretty much if you see like a group 1a or 2a element, it's going to kind of fall under this case where it can pretty much either be an S or an sp, just because it doesn't have enough valence electrons to hybridize far enough. Sorry, I'm going to try to I'm gonna sit here for a second. I don't know if my essay is in a waiting room or not, but I'm gonna explain this first and then go and show it. But okay, so that does give us that sp. Again, that sp, there is two orbitals, each half filled, which does coincide with us forming two bonds, and then we still do have those two unhybridized p orbitals because nothing was ever in them, nothing wants to go in them. They're chilling, right? Okay, over here is the F. I know I didn't write F, but as I literally, it's crazy. I had actually literally just talked about the case for fluorine earlier, but fluorine is a group 7A. Once you do that orbital diagram for fluorine, you will see that it has, that 2s and then five electrons in the p orbital. We can only ever go up to an sp3, correct? I guess we could go up to an sp3 here. Yeah, technically in this case I said no mix because in this case fluorine it really will only well, actually no. I think I did this one wrong. Well, I don't think I did it wrong. I'm about to tell you the right answer. But if you did say that it wouldn't mix, I'm not going to count that. I wouldn't actually. I'm going to go ahead and say it kind of wrong. It does only use this p unfilled p orbital to bond, but as far as this um this unit goes, chapter 11 goes, this could hybridize into an sp3 orbital in which you have four orbitals, but the first three are completely filled. In saying that, like the first sp3 orbital has an up and down, that second square has an up and down, that third square has an up and down, representative of the three lone pairs, which we see over on the fluorine. But that fourth orbital, that fourth square, is still only going to have that one up arrow, just as I have highlighted here. And that is going to be a more accurate representation, especially because it does have four electron groups. It is going to be sp3. So yeah, so I'm going to say we'll write this because this is the initial electron geometry, but when you do mix it, I'm going to say there is a mix, but do go ahead and put that sp3 hybrid orbitals, with the first three being completely filled and that fourth orbital being only half filled, representing that one bond from fluorine to beryllium. Did everyone hear that? Everyone good with that? Everyone understand what I'm saying there? Yeah? Okay, cool. So then my key says that. Again, this is a problem from the book, but it didn't have the full answer for that, and I thought I knew it, but only now am I like, technically I didn't. Hold on, Julia. I know. Hold on. I don't. Oh, do I start sharing my screen for a second? Ah, that's why. Okay. Oh wait, she may not be coming actually. Okay, yeah, she's not coming back. She's her internet's down, but I'm gonna say she was ready to leave. Hold on, let me message her back really quickly, just so she knows I'm not gonna like be mad at her. All right, and then we'll move on. Okay, it's just me now, y'all. I'm probably gonna stop sharing my screen a few times just to make sure no one's coming in because I have to watch the waiting room now. But I think we're doing pretty good. Again, let me know if that one had any questions. Hold on, let me try to find my chat box. There we go. Okay, 11.2. I think this is pretty. Pretty important stuff here. So 11.2, modes of orbital overlap and types of covalent bonds. So orbitals can overlap by two modes, either end to end or side to side, which gives rise to two types of covalent bonds, being that of sigma and our pi bonds. This was kind of a section I was really looking forward to quizzing y'all on a lot of stuff, so I'm really sad the answers are just like literally in front of your faces right now. But yeah, hopefully some of this will try to still quiz you on. All right, so let's look at three specific molecules. It's going to represent the three cases of, really there's only two cases, end to end and side to side. However, we can have a little bit of combination of both. So we're going to have three specific molecules, ethane, ethylene, and acetylene that we're going to be talking about here in a second. Let's go ahead and jump into ethane though. Ethane is going to be representative, or is going to be our poster child, I should say, For our end-to-end overlap as well as our sigma bond, one of my blanks is this little sigma symbol. It's like a little O with like a flat line on top of it. But this structure over to the right is going to be our methane. Everything is just a single bond, so that's pretty easy to work with. So a sigma bond is formed by end-to-end overlaps of orbitals. Of course, you probably could have got that from right here, but I did bold it because it is an important statement. I do know that they did do a little bit more multiple choice on the last test, and because this section is extremely conceptual, I think this exact statement is very fair game for literally like they could like say a pi bond is formed by blank overlap of orbitals and you'd have to know end to end or side to side. It's 50-50 shot, but I do think it is very fair game to ask just because it is literally an entire section of the book, right? Um, okay. So a sigma bond has its highest electron density along the bond axis. So when we're saying that, we're just basically mean like the single bond, it's got that bond part that we're looking at, that is where the highest electron density is. Not too much to really grasp from that. Pretty easy to see. And it is shaped like an ellipse rotates about its long axis. So that's kind of conceptual how I kind of picture it. It's kind of like, oh, that's gonna be ugly, but kind of like an ellipse is kind of thicker on the like middle part, and then kind of gets like skinny but ovular towards the sides, and then kind of gets like thicker on the end. That's kind of how I think of an ellipse. Um, but again, that is kind of how our electrons are. They are more concentrated towards the middle, so we have kind of like a thicker electron cloud. They kind of get skinnier as we get closer to the nucleus because they just don't spend as much time there. So, okay, cool. Oh, let me zoom in. Okay. All right. So another point. Wait, did I skip a page? No, I did not. Okay. Absolutely. Yeah, if you need to go ahead and go, I'm not going to be mad. I understand that people have things to do. Yeah, I'll go ahead and put the page up for now. Okay, but that top left does say that all sigma bonds. Oh, no problem, Ruth. I didn't even. You're good. It honestly may be my internet because my essay got kicked out as well. So, yeah. Okay. Hopefully you got that. Sanhana. I know I butchered your name. I'm so sorry. Oh, you mean the previous page? LOL. Yeah. Oh, no, it froze for you? Oh, yeah. I mean, it's still maybe my internet. Again, I'm at some random hotel. Like, okay, but a sigma bond is always going to be representative of a single bond. We can have sigma bonds in double bonds, but it's always going to be representative of that single bond that we think of, that kind of that just bond to bond. So all single bonds are sigma bonds, and second, well, all sigma bonds are single bonds as well. I'm gonna say all sigma bonds are partially single bonds. Are you road tripping or quarantining? I'm road tripping. I'm in. It's kind of weird. My family goes to Disney World every Thanksgiving. We have a really small family, so we just go to Florida every year. Yeah. Okay. No problem, Caitlin. Thanks for saying. So I think it's gonna be our example here. That's gonna be basically. It's gonna be like this. It's basically gonna have a double bond. Basically, that's all it is. I don't know. Did I draw it anywhere? I didn't. Go ahead and look up ethane if you need to see it though. Basically, it's like a C to C. Am I saying that wrong? No, ethane is a single bond. Yeah, I was going to say I literally think ethylene is the double bond. Okay, yeah, ethane is gonna be the single bond. That's the one that I did draw. I was gonna say I thought I'd drawn all of them for y'all, but okay, ethane is the one that I drew on the past page. Everything's single bonded. The C to C bond is made by the overlap of the end of one sp3 orbital. Hold on, I gotta move my chat box. It is literally in the middle of my freaking stuff, and it's really not moving. Okay, is by the overlap of one sp3 orbital. Again, we do understand that every single one of that carbon is bonded to a molecule. Therefore, it's going to be sp3 because it has 4 bonding groups with the end of the other sp3. So again, the 2 carbons, they're both sp3 hybridized. This is just end to end. A single bond is end to end. It's basically just like they're just lining up. They're just kind of hitting each other. It's just the simplest case that you can think of, really, and a second one we'll see side to side, is really the case where you need to conceptualize it. But end to end, literally just think of it like Lego pieces, end to end. Okay. The C to H bonds are made by the end of a sp3 overlapping from the carbon with the end of a 1s orbital of the hydrogen. So here, again, kind of really hammering these orbitals in your head, but this is the orbital diagram for the carbon. Again, we do have 4 valence electrons for the carbon. We want to spread those out so that so we can form up to four bonds, which gives us the case of sp3. Hydrogen, of course, it is just a 1s1. It couldn't hybridize even if it wanted to, so it's not going to. So it just stays like that. Okay. We see from sp3 hybridized orbitals, the carbon has 4 unpaired electrons, hence it making 4 bonds, 1 to carbon and 3 to hydrogen. Yeah, kind of the main thing to be really noticing, or the thing to be picking up, I guess I should say, from end to end, is that basically we can have a combination, like the end to end is the end of an s orbital to the end of an sp3. The actual bond between a hydrogen and carbon isn't like an orbital. The bond is a combination of orbitals. The bond is a combination of the 1s orbital and the sp3 orbital from the carbon. That's the end-to-end joining. Okay. So next, let's look at the side-to-side hybrid orbitals. So side-to-side overlap and the pi bonding, of course, represented by just the pi symbol. Easy enough. We're gonna have 2 cases for this: ethylene and acetylene. They're both gonna be representing pi bonds, but slightly different. I'm just gonna go ahead and, well, I'm not gonna give away too much, but slightly different cases. So a pi bond is formed by side-to-side overlap of orbitals. Again, I just bolded side to side because I do think this could literally just be a question that can just straight up ask you on the test. So a pi bond has two regions. So from everything else we have been talking about for electrons, everything has been in the same region, the same localized area. Very crucial that you understand a pi bond has 2 regions, or 2 lobes of electron density, one above and one below the sigma bond axis. The 2 electrons and 1 pi bond occupy both lobes. Okay, reread this. The 2 electrons and 1 pi bond occupies both lobes. 1 pi bond occupies both the top lobe and the bottom lobe. So again, I'll try to show this a little bit later. I do think, yeah, we'll see it kind of in this picture over here to the right. But kind of really get that in your head that it's above and below the plane. No longer are we just having electrons in just one central area. And again, this is why this is suddenly getting kind of crazy, because we do kind of have stuff on different sides acting as if it was together. So bear with us for a second. Okay, so a double bond. A double bond is going to consist of 1 sigma bond. That is going to be the case that we were talking about from the ethane, which is going to be the end to end, that just the s orbital going straight on to the sp3 orbital. So a double bond is going to be 1 of those and 1 pi bond. Okay, and both these together, or the double bond, it increases electron density between the nuclei. It kind of makes sense, right? Every bond is representative of a pair of electrons. So if we have a single bond, that is 1 pair of electrons. If we have a double bond comprised of a sigma and a pi bond, that is now 4 electrons. Of course, our electron density increased. We just added electrons. I mean, come on now, right? So I think that's easy to see. That electron density is increasing with increasing bonds. All right, and then 2 electron pairs act as 1 electron group because each pair occupies a different orbital, which reduces repulsions. I'm really not going to go into the details of this, but this sentence is basically just saying, like, this is why we count a double bond as the same as a single bond in terms of like counting the amount of electron groups around an atom. As far as counting groups, a single bond is exactly equal to a triple bond. And that's because even though we have different orbitals being in play to form a bond, they're all acting to reduce repulsion and therefore are kind of complementing each other and increasing that stability. Okay. So, and then therefore a triple bond comprises of one sigma bond and two pi bonds. Oh, that is supposed to say two. Please do not write one pi bond. Please do not. Please write two pi bonds. That is not supposed to be one. That is supposed to be two. Two pi bonds and a triple bond. I hope everyone gets that. Someone in the comments give me a confirmation that you heard me. Okay, perfect. Thank you. Perfect. Thank you, Laura. Okay, cool. Okay, so now let's look at the example. Ethylene is going to be this example. Again, we see this double bond here in the middle. That is the thing we're looking at. And yeah, as well as if we want to count the amount of electron groups, we had just said that a double bond is still just one electron group. So here we see that we have 1, 2, 3 electron groups. So therefore, we quickly know that we're going to want to have an sp2 orbital for our carbon, because we know carbon only wants to have a max of 3 bonding, or yeah, 3 bonds. I guess you could say 4 bonds because it's a double bond, but 3 bonding groups I think is probably a better word to say. So here, okay, I was literally just said it, but each carbon is sp2 hybridized. Again, I think the easiest way is just to count up the amounts of bonds or electron pairs. Again, just 1, 2, 3. So you can think of a subscript or a superscript of 1 on the s. It's like s1, and then p2. So like adding 2. So like we have 3 things going on, right? The 4 valence electrons of carbon half fill 3 sp2 orbitals and the unhybridized sp2 orbital. Okay, so again, we had just looked at ethane where, again, of course, carbon still has 4 valence electrons and it made the sp3. Here, of course, carbon still has 4 valence electrons, but now is going to be making the sp2. So specifically, we want to look at the orbital mixing here. So this is going to, this left side, of course, is the orbital diagram that we've had pretty much all day now for carbon, the 2 and the 2s and the 2 and the 2p. We're going to mix these together. However, we saw there are only 3 electron groups, so we only want to have 3 hybrid orbitals. For that reason, I will just pull down any 2 you want from the sp2, or sorry, from the p, and bring that down to where we can have the sp2 orbitals. Again, we want to have 3 of these. Each sp2 orbital, we want to be unpaired. Now, here's where things are just, I'm just gonna say, out of the norm. I feel like this is why people start to get scared of orbital diagrams, because this is very different than what we expect from Hans and Pauli's. Hans and Pauli says that we must fill every lower orbital before we can start to match them. But as we see on this, oh, this is supposed to be sp2, not 2s2. From this sp2 orbital, none of these are filled, but we go ahead and fill the 2p. That is because even though it is a new orbital, it is so close. It is so close to the energy level of the p that we are practically fooling it, like in the truest sense, fooling it into thinking that they're all equal. And so that for that reason, we will start to see just one going into the p orbital. And again, because we know we want to form 3 bonds, we know we know that those hybrid orbitals must remain unpaired so that they can in fact make that orbital. So okay, again, just my best advice is just determine your amount of electron groups, and then from that you can do this sp orbital thing right here, which should give you sp3, because again 1, 2, 3, or sorry, sp2, because 1 and 1 for the s and 1, 2 for the p2. So again, maybe a little bit of practice, but this is, again, I said at the very beginning of the session, the first time you see this stuff, a lot of times it doesn't make sense. The second time, a lot of times it still doesn't make sense. It's on that third or fourth time where it really does start to click. So if you're still having trouble seeing the difference between when we make an sp2 versus an sp3 carbon, we're gonna have another example here. But
Just go to the book and just look at more examples. They really follow a pattern. So, alrighty. These little blanks are referring to above. So the unhybridized 2p orbital lies perpendicular to the sp2 plane. That is because when we have a tetrahedral electron geometry, which is when we have 4 electron groups, right? Whenever we take an electron group away from that, we understand that we have trigonal pyramidal um or that may not be actually the I'm not sure that is the molecular geometry. I want to say it is, but I'm not actually positive. No, it is. It is. It literally is trigonal planar because you'd have the 3 bonding groups down with your 1 electron pair at the top repulsing everything else down. And from that, we can see that the 2p orbital, well, maybe you really can't see from that, but the 2p orbital does lie perpendicular to the sp2 plane. Again, that sp2 plane is going to be um, flat. It's going to be your trigonal planar. Did I say that wrong? I'm pretty sure. Yeah, it should be trigonal planar. Oh yeah, exactly. And then so from that, our electrons, because it is planar, they can either go to the top or the bottom. And because it's not parallel with our bonds, it therefore must be perpendicular. Again, if we have something planar and we add electron pairs, that must go to the top or the bottom, which is going to make it, yeah, perpendicular. Okay, so 2 of the 3 sp2 orbitals of each carbon form sigma bonds to the respective hydrogen. That is again because hydrogen only is a 1s1. It doesn't it doesn't even have an extra electron to donate to a pi bond or a double bond. So pretty much anytime you see a carbon to a hydrogen, no, it's a sigma bond every single time. It's always going to be a single bond, always going to be a sigma bond. Okay, and then that third sp2 orbital forms a sigma bond with the other carbon. Again, that part, that sp2 to sp2, that is going to be end to end. Still, we're going to see that side to side very soon. Okay, okay, literally right now we're about to see it. A second bond is formed between the 2 carbons. Again, we saw that first bond between the 2 sp2s forming that end to end. But we do have a double bond as we see. So that second bond is formed between the 2 carbon atoms when their half-filled unhybridized 2p orbitals overlap to form a pi bond. So that is why now you can see this 2p here, because that 2p is contributing to the pi bond. Both carbons have this electron geometry right here of this, everything's got 1. And so each, these first, this 1 and 2 of the first sp2 is going to go to the hydrogen. This third sp2 is going to go to carbon to form the first bond, that sigma bond. And then this 2p from one carbon and the other unhybridized 2p from the other carbon, those are going to go into those side to side orbitals and create that pi bond. So again, a second bond is formed between the 2 carbon atoms when their half-filled unhybridized 2p orbitals overlap to form a pi bond. Okay. Let's see, we've got 7 minutes. I think we'll pretty much be done here soon. So acetylene, this is the case where we've got a triple bond instead of a double bond, of course, because we're making a triple bond and carbons only ever want to have 8 electrons. Now we do have just 1 hydrogen on each side versus 2 or 3. So each carbon in this case is going to be sp hybridized. Earlier I had literally said if you see that something is linear, no, right then and there, it is sp hybridized. Easy as that. And its 4 valence electrons half fill the 2 sp hybrids and the 2 unhybrid 2p orbitals. Okay, once again we have this, the left side is just our typical carbon electron orbitals that we've been doing over and over. We mix these together, and again, we see that carbon is only making 2 bonds. It's only bonded to 2 atoms. So for that reason, our SPs is just literally going to be just that S and that P. We only want to have 2 orbitals to form 2 bonds. So for that reason, I only pulled down 1 orbital that leaves two p unhybridized orbitals up at the top. And then just like before, all I do now is just go and fill in my orbitals, just like up here. Not only do we know now that our unhybridized p orbitals are going to form our pi bonds, but we do this because these are so literally so close in orbital energy and distance that it tricks electrons into thinking that these are all equal. So they literally want to act like, for these cases, like they can just go 1 to 1 to 1. And then again, I think we'll see it here in a second. But again, now that we have two unhybridized 2p orbitals, that is going to set up the case for two pi bonds, because this is representative of one for both carbons. Both carbons have this 2p. And so from this, you can see that if we have two orbitals that are unhybridized and the 2p, the other carbon is just going to supplement that, right? Yeah. Okay, now I really, really gotta move my text box. Oh, muted myself for a second. Okay, here we go. So each, and this is referring to the, was it ethene? Ethane? Whatever it is, the triple bonded one. Each carbon forms a C to H bond, or a C to H, sorry, sigma bond with one sp orbital and a C to C sigma bond with the other. So again, it's just sp to sp, end to end. Side to side overlap of one pair of unhybridized 2p orbitals gives one pi bond with electron density above and below the sigma bond. Side to side overlap of the other pair of unhybridized 2p orbitals gives another pi bond. Again, these, as you probably know, these are 90 degrees away from each other. That's not too hard to see. With electron density in the front and back of the sigma bond. The result is a symmetrically cylindrical molecule. Again, we're almost done. We got about 4 minutes, so we're literally perfect on time with me doing it like this. So now I really want to like show you what is like really really happening. So we have A, B, and C. Specifically, well, let's look at A first and let's skip to C. So A here, I'm gonna zoom in really, really close. Right here, we can see it says sigma right here, as well as you see sp to sp. You can literally see this region of darkened, which I think shows that those are literally end to end. They literally met up like a Lego piece going into each other, end to end, easy as that. And then over here, you can also see that this is an sp orbital from the carbon. However, hydrogen, as it's literally just a circle, that's represented that it is unhybridized, just its s orbital, and still that s orbital and sp orbital still are just end to end, because we only have side to side for pi bonds. So, and saying that, let's look at some pi bonds and what does that look like? So it even says right here, two lobes of one pi bond. They're literally on opposite sides. So our single bond is here, and then our pi bonds, our regions, if this is our sigma bond, our pi regions are here and here, and then here and here. So there's basically 4 regions representing 2 bonds. So again, opposite sides of each other. We have an upside for the black and a downside for the black. We have a left side for the red and a right side for the red. That's that side to side. It's literally on this side and this side of the sigma bond. So side to side bonding. We're bonding on the sides. Again, it is really, really weird to think about how that one electron in the red over here and one electron in this other red act as a double bond. Like, it's really weird to me to think of that because they are separated. But again, they do still act like just a bond. They act like they're kind of paired together, which is kind of crazy to me. But I do think it's really kind of important to kind of visually see the difference between end to end and side to side. So hopefully that'll do it. Okay, let's talk about a little bit more and then I'll get you guys out of here. I'm ready to get out of here too. All right, so last point, they will test you on this, I'm pretty certain. A sigma bond is stronger than a pi bond. A sigma bond, again, is the side to side. A sigma bond is, oh wait, sorry. A sigma bond is stronger than a pi bond. My bad. My bad. A sigma bond is the normal singular bond. It is in my head easier to see that it's stronger because it's literally like together versus a pi bond is that side to side. It's kind of like split up into two regions. It's for me is a little easy to see that because that pi bond is split up into two regions, it's just therefore not going to be as strong as the sigma bond simply just based off proximity, which has kind of been a thing we've been kind of talking about these past 3 weeks. Is the closer things are together, the harder they are to pull apart. So kind of same thing for this pi bonds because they have a little bit of separation between their two electrons. It's just not as strong as a bond. And so therefore, because of this, a double bond is actually just slightly less than double the strength of a single bond. So if I have a single bond, let's say it's like 1 kilojoule per mole, we're pretty much saying that a double bond is really like 1.75 kilojoules per mole because we're saying that single bond is still that 1 kilojoule per mole, but that pi bond, that new bond from the side to side is weaker, let's say about 0.75 kilojoules. So when we add that together, it's 1.75 kilojoules for a double bond versus if we had just two sigma bonds, two single bonds, that would be, 2 kilojoules. So just kind of interesting to note that just a double bond isn't directly double the strength of a single bond. Okay, and then here's this. I'm gonna go ahead and kind of let y'all take a photo of this. I did break this down into, the equivalents. Do note that every single one of these hydrogens is equal as well as the two reds are equal. That's because this is a completely symmetric molecule. So if we literally fold it in half, we would see that the two reds are on top of each other and the two or all three hydrogens are on top of each other, representing that they are literally the exact same in every chemical thing we could measure. So that's why basically I just like for the red ones, I just went ahead and like highlighted it just so I can say like this is representative of all of these. Can I get me to scroll up? Absolutely, yeah, I'll just kind of scroll out really. But okay. Absolutely, Mackenzie. Absolutely, yeah. I'll go through all the pages in a second. But I do want to kind of talk about this. Okay, this first carbon, we see that it has three groups, so therefore sp2 and one unhybridized orbital. Again, sp2, that's always going to leave a p orbital because we have three orbitals in the p. If we only pull down two orbitals, we have one unhybridized. The red C's I think are super easy to see they're sp3 hybridized. One thing I do want to note is that it's sp3 to sp3 bond for the carbon, that's end to end. Hydrogen, it's always going to be 1s in pretty much in all cases. So therefore, it's always going to have a sigma bond with an sp2 to carbons because again, I should say sp3. This should say sp3 while I'm thinking about it. Before y'all send out that key, Ruth, Miss Ma'am, you better correct that to an sp3 right now. Okay, you better listen. So with an sp3 carbon. No problem, Laura. Thank you for staying so long. Hope to see you next week. Here, the oxygen, again, it's got 1, 2, 3 electron groups, so it's going to be sp2. It does have a pi bond with an unhybridized p orbital from the carbon. Again, both, as we see, carbon up here has one unhybridized p orbital, as well as so does oxygen. Again, we can see this from that sp2, that they'll both have a p orbital, which gives us that case for that double bond. And then two lone pairs lie in the sp2 orbitals. Again, anytime we have lone pairs, yeah, this one should be sp3. This one right here that my little mouse is on next to this red C should be sp3. But yeah, anytime we have lone pairs, those are going to always fall into a hybridized orbital. Always. Just always. So, but yeah, guys, I'm going to scroll through the packet. Again, sorry for my iPad not working today. I literally hate that for me. I hate that for you. I think it still went pretty okay. I think I explained most of this probably well enough. I think this is definitely a subject that in lecture you just don't get. I mean, I literally didn't even know we had talked about orbitals in 1307 for quite a while. So hopefully this at least gave you a good working knowledge. And again, if you haven't seen this stuff yet, or maybe you just saw it today, hopefully we'll really get it ingrained in the next few days. Let me see if my if Miss Ruth is still here. Perfect, y'all are. My regulars are still here. So while I'm here, I'm probably gonna end the session probably in the next like 5 minutes, just because I'm ready to go to bed because it's literally 10:04 here. I'm doing test prep or exam prep next week. What do y'all want to see? Like just straight up, what do y'all want to see? Which exam would you want me to test over most or give you most questions? Do you want just practice days? Do you want just conceptual days? Do you want me to continue teaching with 11 and 12? Like I don't know what y'all want. Thermochem, so that's definitely exam 2. Yeah, I figured exam 2 is going to be the more popular opinion to kind of state. But I really want y'all to decide um, more than me, because if it was up to me, I'm probably gonna have just one crash course day, probably focusing mainly chapter 2, maybe a few things from chapter 1 and chapter 3. Can you see the next page? Yep, absolutely. And then probably a test prep or a practice problem day, but I would really like to hear from y'all and hear if y'all want to see more of chapter 11 or more of chapter 12 or specific concepts. So, yeah. I guess what I'm going to say now is it doesn't seem like a lot of y'all are super confident on what y'all want to see yet, but you have till next Monday. I'm sorry for like laying my head on my pillow so much. But if you randomly anytime throughout this week think of something you want, or you're just like, I really would like for him to talk about chapter 12, just send me an email. Just be like, hey, can you fit section blank in for me, or can you fit in bomb calorimetry for me? If you send me an email asking for something specific, you're probably going to be one of like 10 people who does that. So more than literally certainly, if you send me you want something, it will make it into my packet. So if there's something you know you're not strong on and you want to see me say it, send me an email and I will I will put it in the bag for next week. So yep, exactly, Ruth. The final is over everything. It is comprehensive. You're on vacation mode? No problem, Ruth. Me too. Literally me too. Me too. The burnout has been real, y'all. Literally, I got a 66 on a test last week. I haven't failed an exam in like I don't know how long. So yeah, I'm really scared for everybody because I don't normally get burnt out. So for me to be like this burnt out and like making bad grades, I know as like a lot of y'all are freshmen and that the burnout for first semester can definitely be real. So you only got 1 week left, so I know we're all burnt out, but literally give it everything you got. Really. Like, give it your all, and then once it's over, literally sit back, take a deep breath, and just say, I did it. So, yeah. I hate it here too, Joyce. I hate it here too. But it is what it is. Hopefully next semester will be better. I don't think it's gonna be much better. Hopefully y'all's classes are better, but as far as like COVID and just everything just being this way, in my opinion, is contributing to burnout, and I don't see that being much different next semester. So I hope it is, but we will see. Yep, exactly. It's the only session this week. Yep, I will have sessions next Monday and Wednesday though. I hate COVID too. It really does suck. I'm in Disney World right now, and it is just not the same. Like, I mean, it's still fun. Of course, it's Disney World, but it's not like Disney World, you know? Like, I don't know. I know that sounds really spoiled to me because like most people aren't even going anywhere and COVID's ruined everything, but COVID has just really ruined everything. Like it just is so annoying. Like I don't know. Like I just miss like even seeing my friends in class. Like I don't have a lot of friends outside of class, so like I like rely at times on like seeing my friends in class for like my social interaction. It's like just like not even having that this year has just been like really tough. I think that's kind of why I've like kind of leaned into y'all a lot this semester of like being like open with y'all and like being super talkative just because I mean I need someone to talk to too, you know? So and COVID's really taking that away from me at times. Lockdown is gonna be rough. I foresee it coming soon. Yeah, I'm here stressing about the iPad and Link. I'm stressing about the iPad and Link because I expect like literally 100 of y'all to expect that shit to be right. And so from my Link to not be working and then my iPad to literally be crapping out is extremely embarrassing. I mean, it is pretty unprofessional and just straight up embarrassing. So I do stress about that kind of stuff just because while I am my own person, I do know that a little y'all do kind of rely on me to have my P's and Q's in order. Like, again, I literally send an email to 1,500 people. What I say to them, they pretty much expect to be true. So I do stress about that kind of stuff. Sarah's gone, but thank you, Sarah, in spirit. Yeah, well, I mean, yeah, and neither of them were my fault. I mean, I'll throw Michaela under the bus. Only got seven of us here. Michaela did mess up the fucking link. She did. It makes me mad. It literally makes me mad. But she did. iPad, I have no clue what's wrong, but whatever. It is what it is. Hopefully, my test preps will be absolutely bomb, and it'll all be okay. But it did suck today. It's kind of a downer, but I'm gonna be okay. I'm at the happy place or something like that. LOL. Yeah. I mean, it's still. I mean, it's still the happiest place on earth, but just not. It probably is still the happiest place on earth, but not as happy of a place as it used to be. You know what I'm saying? Like compared to the places on earth you could be with COVID right now, it probably is. But it is just different. It really has been a crazy day. Legit saw these cops catch a guy. Oh my god, that is intense. But we love a good cop scene. I used to literally be obsessed with the show Cops. Like had them recorded, everything. And they discontinued Cops when Black Lives Matter and George Floyd came out for good. I mean, I am not getting into politics. I'm not gonna say for good reason, but I do see why they did it. I mean, it is just controversial. I'm not getting into the politics of it. I'm literally not. But it did break my heart that they took off Cops from the from the TV program. But that is kind of crazy. Glad you're okay. Glad you didn't get involved. But I'm just rambling at this point. I don't have my man's here. My man's is coming tomorrow to Florida, so I'm here all alone tonight. So I don't know. I'm just rambling to ramble. But does anyone need anything else in the packet? I'll go ahead and show it up one more time. But I'm probably gonna call it here. Of course, Ruth. You know I love you to death, Ruth. So have a great break, Ruth. Actually, I forgot to tell everyone to have a great break. I forget it's literally break time. But yeah, everyone have a damn good Thanksgiving. Go eat a shit ton of food and just go relax for me. Like I know we could all use it. So yeah, I love you so much, Joyce. You're too sweet. I will have fun. But yeah, all y'all, all my regulars, y'all know I love y'all to death. Y'all have treated me like way kinder than I expected this year. So yeah, I'll see y'all. I'm probably about to end the session. Well, I'm gonna go and stop sharing my screen. But yeah, everyone have a good Thanksgiving. And yeah, thank you, Joyce. That is really sweet. That is actually really sweet. Didn't say, you love me from day one. I don't know what I did. I really don't know what I did, but I appreciate y'all. Really. Like, y'all would probably be shocked the amount that I literally tell my boyfriend, like, how humbling it is to have, like, people say such kind of words to me all the time. Like, it really at times does, like, choke me up. Like, I mean, I do get emotional sometimes on here, but I'm normally pretty tough, but y'all really do choke me up sometimes. Y'all are way, way, way sweeter than y'all need to be. So, well, thank you, Joyce. But yeah, I mean, I just wanted to be different. I've always been different. I think it's super important to just be different in front of a typically freshman course. I know obviously not everyone here is freshman, but I do think it is important to just be 100% me at all times. So I think that's what I did, and I think that's really, I mean, that's what I attribute to me having the success is just being real and just trying to be one of y'all and being relatable. So I don't know, but thank y'all, really. So yeah, that's really sweet, Ruth. I appreciate y'all. Ruth, I love you to death. You didn't invite me to play Among Us this weekend, so I'm a little mad, but I'm just joking with you. But do invite me sometime. I would actually really like to play. But I'm gonna end it here. Hey, I won that game too. Hey, hit Ruth up. She's coordinating. You went to a concert Friday? I see. Well, that was fun. That was probably better than Among Us, anyways. But let's do it sometime. Semester's about to end, and truly enjoyed you guys. It really is sad that it's about to end. And I'm going to bed, Ruth. I'm literally going to bed. But once semester is over, I don't want to say bye to literally so many of y'all. So let's keep up. Let's do something. So yeah, I am gonna end it here though. So yeah, let's do it. Me, you, and Joyce, Ruth. Let's all do it. But I'm gonna end it here. Everyone, go have a good Thanksgiving. I'll see you on the other side next week. And yeah, bye y'all. Deuces.